When we look at exponential growth and decay, we are looking at a relationship that changes by a multiple. So doubling represents an exponential growth in that case. Halving something represents exponential decay. It also affects percentages. When you're taking 50% of something, then you're doing a multiplication problem. Percent of, whenever you see that word of, it means multiplication. Now, no matter what, whether you have growth or decay, all exponential functions have the same basic equation. Y equals AB to the x. I'm going to refer to A, B, and x in terms of situations. They mean something more specific when all you're doing is looking at an exponential function. But for a situation, A represents the initial amount in that situation. If you had something that was doubling, what you started with is the initial amount. What you doubled, that's your growth or decay factor, which is B, the base of the exponential problem. The last thing that we have is the x. X represents the number of times it goes through that multiplication. How many times does it get doubled? How many times does it get cut in half? Now for our growth or decay factor, we can think about this in terms of the percentage. We always start out with 100%. If you're doubling something, how much are you adding? You're adding another 100%. So we have 1 plus 1, and so inside our parentheses for the b, we would have 2. Something's doubling, that's why we use a 2. Something's getting cut in half, you start out with 100% of it, and you're taking away half of it, or 50% of it. So then, when you have a half, 1/2 would be your b. So you can think about this with percentages. If I said, oh, it's increasing by 9%, we would have 100% plus the 9%. And we might have 100% minus if something was going down. So whenever we have a percent problem, we have to remember that 1 plus or minus the percentage. And that will tell us our growth or decay factor. So let's use this in some examples of situations that involve multiple changes, some exponential growth and decay problems. Before we start looking at any situations, I want to look at just a generic exponential, just so we can practice using y equals ab to the x. So we know that our exponential function is going to be in that form. And we're given a little bit of information. We know b is 7, and we know the point 5, 3, 43. So remember, when you're given a point, you're given an x and a y. And b, well, we see where b goes in the equation. Before we start solving anything, let's answer some questions about b. B is 7, which means we have a growth problem. And we could actually say by how much percentage we're growing to. You always have 100%, and you're adding 6 to that, so it's growing by 600%. Which kind of makes sense when you look at the point that we were given. That's a pretty big number. So let's go ahead and use the given information, plug it into our exponential form, and see if we can find the specific equation for this situation. 343 is y equals a times 7 to the 5. Alright, well now it's just a matter of solving for a, so it's a matter of using algebra. So first thing we need to do is raise 7 to the 5th power. So you have 343 equals a times 16,807. Divide both sides by your 16,807. And here's where you'll want to have a calculator to help you. Yes, you can simplify that fraction yourself, but you can also simplify the fraction if you're using a calculator like a TI Inspire or something that helps you go from decimal form into fraction form. And so in this case, when we do that, we get a equals 1 over 49. We want that because we want to write our equation as y equals 1 over 49 times 7 to the x. And so we want to have it in fractional form, that way we have the most precise answer. So let's look at just one more like this before we start really looking at specific situations. Say we have y equals ab to the x. That's a given because it's an exponential problem. We know b and we know a point. So we know an x and a y. First, let's look at our b. Is this problem a growth problem or a decay problem? It's decay because it's smaller. It's smaller than your 100%. So our decay is, well, how much smaller than 100% is it? It's actually 80% smaller. Because 1 minus 0.2, that's an 80% change. So let's go ahead and find the specific equation for the situation with an 80% change. We know y equals ab to the x. So we can use just basic evaluation to finish this up for a. 0.2 to the negative 2 is 25. Divide both sides by 25. And we should have our value of a. So a in this case equals 3/5. That means our specific equation is y equals 3/5 times 0.2 to the x. Now, I just wanted to do these first couple problems so we could get familiar with our y equals ab to the x form. All the rest of those problems in this video are going to be looking at examples, more specific examples of growth and decay, especially when it pertains to situations. So here we have the number of bacteria in a dish are doubling each day. We have 4 bacteria originally, and we want to know how many there will be in a week. So let's think back to our equation. It is y equals ab to the x. And on the first slide, we talked about the fact that a represents the initial amount, b represents the growth or decay factor, and x is the time. How many times does it go through that factor? So if we plug in what we know that y equals 4, because that's the initial amount of bacteria, times 2, if it's doubling, it's going up by 100%, 100% plus 100% is 2, to the x, and in this case it's a week, so x is actually 7. So 4 times 2 to the 7th is going to tell us how many bacteria there will be in a week. We want to get our handy-dandy calculator out to help us with that, and we get 512. Copy machine reduces the size of an image by 1/3 every time through. If an image with dimensions of 8 by 12 is run through the machine twice, what are its new dimensions? Alright, this one's a little bit trickier. Let's start out our equation, y equals ab to the x. And initially, I know 2 different things. So I'm going to need 2 different equations. We're going to need a equation for the dimension with the 8, and we're going to need an equation for the dimension with the 12. So I'm going to write 2 separate equations. Everything else will remain the same though. When we read this question, it says it's reducing the size of an image by 1/3. So our growth rate or decay rate needs to reflect what is left over. So we're reducing by 1/3. We're taking 100% of it, reducing by 1/3. What's left over is 2/3%, or 2/3 of it. So that finishes off our equation. 2/3 is the decay factor. Now, it's run through the machine twice, so the number of times is 2 in each case. So now we just need to do our 2 calculations. 8 times 2/3 squared and 12 times 2/3 squared, and we'll get our 2 new dimensions. So 8 times 2/3 squared gets me a fraction, 32/9. And since this is a copy machine, it's probably going to convert it to a decimal, which is about 3.56. In the second dimension, 12 times 2/3 squared. Again, we're going to get a fraction, 16/3. And again, I'm going to simplify it into a decimal, so let's say 5.33. So the final dimensions of this picture are 3.56 by 5.33. It's been reduced a couple times, reduced by 1/3 each time. So a diamond ring was purchased 20 years ago for $500. The ring has increased by 8% each year. We want to find the value of the ring today. So let's think about our y equals ab to the x. We can plug in what we know. We know that we have 500 initially, and we know that it started at 100% of that value, and it increased by 8%. So it's 1 plus 0.08. You would want to change it to 0.08. That's how we would write 8%. It's really 8/100ths. Then to the time, well, how many years have passed? How many chances has it had to increase by 8%? 20. So that's our exponent. So we can write this as y equals 500 times 1.08 to the 20. But what's really nice, there's a couple online calculators as well as a lot of the handheld calculators out there that you can type in this exact form of the equation and it will evaluate it right out for you. You can do the same thing with this one too. Comes in very, very handy, especially when you're looking at fractions. So we want to grab one of those calculators. I'm sure your facilitator has told you where to find one. We're going to type in our information so we can figure out how much our ring is worth today. When we type that in, we get, $2,330 and approximately 48 cents. So the ring is worth a pretty penny by now, and it's only increased 8% each year. That's what's so powerful about exponential stuff, is it changes very quickly, very rapidly, once your years or your time gets higher. So the number of deer in a park are decreasing by 12% every 6 months. There were initially 230 deer. How many will there be in 3 years? So let's go ahead and get ready to start plugging into our equation, y equals ab to the x. Initially, there were 230 deer, and it is decreasing by 12%. So we're starting with 100% of the deer, and we're taking away 12%. To the time. Well, this one's a little bit trickier. It decreases every 6 months. And it's going to decrease for 3 years. How many times does it have a chance to decrease? It's not 3 this time. It's 6. Because it will decrease twice every year. For 3 years, it has a chance to decrease 6 times. So that was a little bit tricky in this problem. That's why you need to think about, what does that x really represent? It represents how much it how many times it decreases, or how many times it increases. So we end up with y equals 230 times 0.88 to the 6. Remember, if you have your handy-dandy calculator, you can plug in either form. I like seeing it in the second form, though, so I can see, yes, this is decay. I do have the correct formula. And we can plug those in and figure out how many deer there are going to be in 3 years. So we do this, we end up with 106.81. And then we want to ask ourselves, are we really going to have 0.81 deer? So we can go ahead and we can round. You can just use standard rounding. People argue with you sometimes when you're talking about growth, decay, but let's just make it simple. Standard rounding. We'll have approximately 107 deer left in our park after this sad 12% decrease every 6 months. So each hour, so that's every 1 hour, the amount of ibuprofen in a person's system decreases by about 29%. After 6 hours, there were 52 milligrams left. How many were taken initially? So let's go ahead and get started with our problem. Y equals AB to the X. we know that there are 52 grams right now. And I know that's not the initial amount, but let's go ahead and let's plug that in because we're going to do this problem a little bit differently. Because we are wanting to go back in time, we're wanting to say how many were taken 6 hours ago. We're going to have to alter our equation a little bit. So we have 52 right now. And we know that it was decreasing by 29%, which means it's 1 minus 0.29. Now, if we're going back in time, we didn't multiply 6 times. We're going -6. What happened 6 times ago? So for our exponent, it's going to be -6. We can write this a little bit more simple if we want. We can say y equals 52 times 0.71 to the -6. Either way, remember that thing I told you about those couple cool calculators. You can type in either of those into the calculator, and we can figure out that 6 hours ago, initially, about 405.93, which is approximately 406 milligrams of ibuprofen were taken. Now let's think about this. The amount of ibuprofen is decreasing. We wanted to find out how much was taken initially, and we knew that after 6 hours there were 52 left over. So does it make sense that our answer is bigger? Yes, we had to have more in order to decrease down to 52. That's what that negative exponent did for us. It made our answer a little bit bigger, going back in time, even though we were decreasing. So just sort of to hone in on the growth and decay part of these problems, it becomes sort of old hat to type in, I know what the initial amount is, I know how the change is, I know the time, but what is tricky is figuring out by how much it's changing. So we're just going to look at some generic equations. We have y equals 3 times 6.5 to the x. That is our growth or decay factor. Well, this is getting bigger. We have 100% and we're getting way bigger. So this is a growth problem. If we were to say by what percentage are we growing, think about we have 100% and we are going to get to 6.5. We're adding 5.5. So that would be 550% when we write it as a percent. I'm going to look at the one next to it, 1/4 times 0.91 to the x. This is decay because we had 100% and now we're less than 100%. And we are less than 100%, so decay. We're less than 100% by about 0.09. So this is a 9% decrease. Y equals 2 times 0.25 to the x. Also decay, because it's smaller than 1. How much are we decaying? Well, it looks like we're going from 100% to 25, so the decay is 75%. And the last one, y equals 0.25 times 3 to the x. 3 is pretty big, so that's another growth problem. If we want to think about our percentage, we had 100%, and we have to get up to 3, we're adding 2. So we are adding 200%. Another way to think about this one is tripling. You can call it tripling, or you can say adding 200%. Either way, it's a growth problem. So for basic exponential growth and decay, it's really just a matter of plugging values into the formula, looking for the initial amount, looking for the growth or decay factor. When it's a percentage, you need to remember that 100. And then inputting the time as the exponent.